Thank you for the introduction. Today, we propose Zensei. It's a technique for seamless and implicit user identification on everyday objects using bioimpedance sensing. So as objects are becoming connected, shared, and smart, it will be increasingly important to personalize their experience for each user. Recognition procedures would, however, benefit from being transparent to minimize interruption, such as prompts for password, PIN, or fingerprints. And such procedures might also create unnecessary complexity for tasks with limited privacy implications, such as a cursor adjustment. So, do we really need iris recognition for just adjusting cursor? So we are also seeing increasing use of multi-factor authentication, where the combination of a secret, such as password and PIN, and physical item provide access. We envision that implicit user recognition could also simplify such scenarios. And Zensei works by measuring the bioimpedance between multiple points on the user at a wide range of frequencies. Each combination of points and sensing frequency is used to build up a set of characteristic curves representing the amplitude and phase response of the individual body. Because Zensei's sensing system uses a tiny alternating current, its sensing electrodes do not require direct skin contact. This allows it to be used in scenarios where clothing or objects will typically interfere. With Zensei, we can build a wide set of applications in the real world, and we can create shared workspace or kiosk experience by just placing a hand on a table or furniture that recognize users, or seamless phone unlocking system or shared smart devices. We were inspired by related work around capacitive and impedance sensing. Please refer to our paper for complete discussion of related work. Diamond Touch used capacitive sensing to disambiguate the users based on their electrodes that their bodies are touching or sitting on. We can also use electrical impedance tomography for hand gesture recognition. Our earlier work, swept frequency capacitive sensing, used capacitance for a wide range of frequencies for hand and body gesture recognition. There are also various conventional biometrics, such as fingerprint, iris, voice, gait, or vein. And body print used a smartphone touchscreen as a capacitive image sensor to scan user body parts, such as ear. And Cornelius and Corrick used a wrist-worn bioimpedance measurement device that tracks whether the device is being worn on the same user or not. So with Zensei, we focused on embedding multi-electrode bioimpedance sensing capability to existing objects, such as smartphones, car seats, and furniture. First, we created custom wireless bioimpedance hardware that measures both amplitude and phase in a compact form factor. Second, we proposed 3 form factors where unique electrode configuration enables implicit user recognition. And finally, our longitudinal data collection and analysis provide insight into how these form factors perform. To enable this new method, we designed custom electronics that could perform multi-electrode bioimpedance sensing with amplitude and phase. So here's an example snapshot of the captured impedance. And in this case, the electrodes at the thumb is connected to the ground, and electrodes at all other fingertips and palm are connected to the signal sensing electrode one by one, as illustrated in these 5 different colors. By rotating the ground electrode, we can have 6 different rotations and a total of 30 electrode pairs. And there are 3 main functions on our custom sensor boards: signal generation and switching and capturing signal. And up to 8 electrodes can be connected to our sensor board. And we have 2 versions of hardware, and the first version on the left was used for evaluation. And it's a custom PCB that interfaces the evaluation board of the NXP ARM Cortex M4 chip, and version 2 is our redesign in a credit card form factor. It has Bluetooth, and micro SD, LiPo battery, and many other improvements. And we implemented a wireless demo using a smartphone with this version 2 board. We designed and developed prototypes to demonstrate 3 different form factors that evaluates and exhibit Zensei's potential. And our goal was to explore how Zensei could be embedded in mobile devices and in future where in furniture where grips, posture, and clothing vary. And for reference, we also designed a handpad with more restrictive alignment, which we expect to provide the most consistent performance. The smartphone allows variation in grip, but ensures robust skin contact. The chair is our most flexible form factor, which will have variations due to changing posture and clothing, and is used to demonstrate the potential for completely implicit sensing. So here is the actual live demo with the 3 form factors, and all of these are running in real time. The sensor board is measuring the impedance between 2 electrodes among their 6 electrodes. Then it rotates the pair rapidly to capture the complete profile of the hand's electrical property. You can see that the user's name is displayed by just pressing a hand. As previously discussed, so each user recognition is based on 9,000 measurements in total. And we added 6 electrodes on the size of a smartphone. By just holding a phone, it detects who is the user. The significant advantage of our sensing approach is that the sensing works through clothing. So direct skin contact is unnecessary because the sensor uses alternating current. This is a powerful feature that can make ordinary objects, especially furniture, user responsive. So we can use this technique to make a car seat intelligent, for example, so that it will adjust seat height, or mirror angle, and radio channel for you in the context that you are sharing a car with your family member or a small group of people. And finally, I will describe the evaluation of our system with long-term data collection over 22 days. We built a data collection kiosk in an office building and 3 stations for 3 different form factors. All of them have dedicated sensor boards and computer. And this is the overview of Zensei's data collection and processing pipeline we used. We recruited a large group of subjects through a user testing agency. The data was collected over 22 days. And each subject was asked to provide 30 samples per day, and 10 samples for each leg, and 5 in the morning and 5 in the afternoon. And we were able to collect data from diverse 46 subjects. The data of raw data of amplitude and phase response between 1 kHz and 1.5 MHz were recorded. The captured data was then used for evaluation. The data was smoothed using a moving average filter, and then user classification was done using machine learning SVM classifier with SMO implementation. And we chose 4 methods to evaluate our system from different aspects. And I will explain them one by one in the following slides. So in this talk, I can only highlight some of the key results, so please refer to the paper for the complete result of the experiment. So first, we evaluated using data from all of the 22 days. We trained the classifier using data of 21 days, then evaluated the classifier with the remaining 1 day. And we got high classification accuracy, especially for handpad, around 95%. And for phone chair, the accuracy was relatively lower because the posture of the hand and body changes slightly every time. The false acceptance rates are very low, which is good, and it was less than 0.5% for handpad and about 1% for smartphone, and 2% even for chair condition without direct skin contact, and subjects wear different clothing every day. And false rejection rate was also acceptably low. So to summarize, so even with variation with postures and clothing changes, and chair reached to nearly 80% accuracy, and as expected, with more consistent and aligned grip, phone reached 90% and handpad for 95%. The next condition is a buffer training. So we trained the classifier with different number of days to see how much data we need for scenario with a rolling buffer. The results suggest that the performance stabilizes after 9 days of collected data. Next, we investigated how unique is this bioimpedance information across users. So we compared the performance with different group size. And handpad and the phone had a good performance for groups of 15 people or less. And chair condition had the least favorable result among the 3 form factors, and this is because the garment changes every day. And we expect that the performance will be more robust and consistent in more specific scenarios, such as commercial drivers wearing uniforms. And finally, investigating the number of electrodes. So we compared all the combinations of electrodes for different number of electrodes. The green label shows the most important electrodes for classification when using a different number of electrodes for classification. And we found that 3 or more electrodes provide sufficient performance in most cases. And here, consistent mechanical alignment is important, and also the choice of the electrode position is very important too. Okay, to summarize, so Zensei works with relatively small groups, less than 15 people. It is good for household or small work team, which might be sharing a car, or mobile devices, video game, or entertainment system. We have shown that the best performance is achieved when we control the alignment with the handpad. This, however, enforces a specific alignment which is limited in the same way as fingerprint readers work. However, Zensei's potential is especially in implicit sensing with no explicit user action. So our mobile device examples show promising results also when aligning varying grips. With the chair condition, we show that our technique also works through clothing without skin contact. And with accumulated training data over multiple days, it also shows increasing robustness against clothing changes as well. Okay, to summarize, so today we introduced wide spectrum bioimpedance sensing for implicit user interaction. First, we designed and built custom wireless bioimpedance measurement device, and then we proposed 3 form factors with Zensei. And finally, our long-term and large-scale evaluation showed the feasibility of Zensei and design guidelines such as group size and form factors and electrode alignment. And here are future works. So we are working on implementing Zensei in real objects and conducting and conduct more long-term evaluation with wireless devices to track everyday usage. We can reduce the cost and complexity and also computational cost by optimizing the system with custom ICs and optimized electrode arrangements and selecting signal features. We are also interested in implementing multimodal sensing by combining other user recognition systems to add more reliability or transparency. We already started some effort to realize the future work, so we integrated Zensei and edge sensing electrodes into custom housing smartphone case. The case's round shape allows us to measure both the user's tissue property and grasping style simultaneously. And we designed a pattern of 8 electrodes arrangement with conductive paint. The Zensei enabled case communicates via Bluetooth with the smartphone. The entire system, the data capture and signal processing, machine learning, are all running on this microprocessor and under the app. So it demonstrates that we can create embedded user recognition system for ordinary objects. Okay. So today we presented Zensei. So it's an embedded multimodal multi-electrode bioimpedance sensing for implicit ubiquitous user recognition. And we also showed you a small set of applications. So our ultimate goal is to make the physical world more interactive, and we hope this project will help pushing toward this direction. And thank you for listening.
Very cool indeed. Thank you very much. Is anybody got any questions?
You mean two users